In today's video lecture, we're going to finish this packet of notes by considering some applications of Thevenin's theorem. The first one is talking about resistive loading of Thevenin equivalent circuits. As we mentioned earlier, one of the advantages of Thevenin's theorem is that if you have a changing part of the circuit, for example, different loads that you're considering, rather than reanalyzing the whole circuit for each load, what you can do is replace the whole circuit except for the load by its Thevenin equivalent, and then you have a much simpler circuit that you can analyze by analyzing the simplified circuit for each of the loads that you want. This is particularly useful when you want to calculate the power absorbed by a load in a circuit. What you can do is replace the rest of the circuit except for the load by its Thevenin equivalent. Then you put in your various loads into the simplified circuit and you can calculate the power. Well, how do you calculate the power? The power absorbed by the load is the voltage across the load, VL, times the current through the load, IL. Using the simplified Thevenin circuit, the voltage across the load is just a voltage division. It's the load resistance over the sum of the load resistance plus the Thevenin resistance times the open circuit voltage VOC. Likewise, the load current is nothing more than the open circuit voltage divided by the sum of R Thevenin plus RL. Power, of course, is voltage times current. So the power absorbed by the load is RL over RL plus R Thevenin squared times VOC squared. An interesting observation is what happens as you increase or decrease RL. Look at the voltage first. As the load resistance goes up, what happens is the voltage across the load goes up. And this makes sense because the load resistance becomes a higher percentage of the total resistance. What about the current through the load? As the resistance of the load goes up, the total resistance also goes up, and because current is voltage divided by resistance, we see that the current absorbed by the load goes down. So as resistance goes up, voltage goes up. As resistance goes up, current goes down. What about power? What happens to power as the resistance goes up? This one's not as clear, because power is voltage times current. If one of them is increasing and the other is decreasing, what happens to the power absorbed by the load? Let's do an example and make some observations. After that, we'll develop something called the maximum power transfer theorem, which is based on Thevenin's theorem. So in this problem, we're asked to determine the power delivered to the load for 5 different load resistors, 2, 4, 6, 8, and 10 ohms. So basically, we're going to keep the rest of the circuit the same. And we're going to plug in 5 different values for the load resistance and calculate the power in each case. Remember, the power absorbed by the load is the voltage across the load, VL, times the current through the load, IL. We will utilize Thevenin's theorem in order to solve this problem. From before, what do we know? We know that the Thevenin equivalent circuit of everything except for the load is a 24 volt source in series with the 4 ohm resistance. So basically, as far as that pink load is concerned, everything else in the circuit looks just like that. So now, when we add our RL, we can calculate its voltage, its current, and its power from 3 simple equations. The voltage across the load from voltage division is RL over RL plus 4 times 24 volts. The current through the load, IL, from Ohm's law, is just 24 volts divided by 4 plus RL. So the power absorbed by the load, which is nothing more than its voltage times its current, is what? We're going to get 24 squared in the numerator. We're going to get an RL in the numerator. In the denominator, we're going to get an RL plus 4 quantity squared. This is for this specific example. In general, the equation we get for the power absorbed by the load, open circuit voltage squared times the load resistance all over the load resistance plus the Thevenin resistance squared. So let's now plug in different values of RL into this equation here and see what our power is. we'll set up a little table. We have RL, we have the voltage across the load, we have the current through the load, and we have the power absorbed by the load. When RL is 2 ohms, we plug 2 ohms into this green equation. We're going to get 8 volts. We plug 2 ohms into this blue equation, and we're going to get 4 amps. If we plug 2 ohms into the equation in pink, we're going to get 32 watts. We also get 32 watts, by the way, by multiplying 8 times 4. Let's do that again when RL is 4 ohms. The voltage across the resistor, in this case, is 12 volts. The current through the resistor is 3 amps. The power absorbed by the resistor is 36 watts. Notice what happens. As resistance goes up, the voltage goes up, the current goes down, and in this case, the power went up. That was the thing on the previous page that we weren't sure what was going to happen. So in this case, increasing the load resistance from 2 ohms to 4 ohms caused the power to go up. What if the load resistance is 6 ohms? Now, we measure the voltage, you would get 14.4 volts. Once again, it goes up. The current is 2.4 amps. As expected, it continues to go down. And now the power, multiply the voltage times the current, or use the equation in pink, you get 34.56 watts. So notice the power went down from the case before. When you set RL equal to 8 ohms, the voltage across it is 16 volts, continues to rise. The current through it drops to 2 amps, it continues to drop, and the power absorbed is 16 times 2, or 32 watts. So the power goes down in this case. Final case, when our resistor is 10 ohms, the voltage across it is 17.14 volts. It continues to rise. The current through that resistor is 1.714 amps. It continues to drop. And the power absorbed by that is 17.14 volts times 1.714 amp, which is 29.4 watts, which continues to drop. In fact, if we continue this all the way to a very, very large infinite resistance, that would be an open circuit condition. What's the load voltage now? Well, by definition, VL, if the load is an open circuit, is VOC, which is going to be 24 volts. That's going to be the maximum that the voltage is going to be. Of course, when you have 24 volts across it, because it's an open circuit, what's the current through it? It's going to be 0 amps. And so the power absorbed is 0 watts, which obviously is much lower than what it was before. So here I did this for 5 different values of RL, but you could do this for as many different load resistors as you want. The question is, for what value of load resistance is the absorbed power going to be maximum? Now we only did it for 5 resistors. For these 5 resistors, it just so happens that the 4 ohm resistor was the one that gave us the maximum power transfer to the load. But we want to ask a general question. In general, what value of RL will give you maximum power transfer to the load? That is what we will look at next. So in some applications, it's desirable to maximize the transfer of power from some circuit or subcircuit to a load. What we saw in the previous example, if you increase the load resistance, its voltage will go up, which should tend to increase the power it absorbs, but its current goes down, which tends to decrease the power absorbed by the load. So since PL is the voltage across the load times the current through the load, the question is what value of load resistance will maximize the power it absorbs? Turns out the solution is very elegant. If you set the load resistance equal to the Thevenin resistance of the circuit it sees, that maximizes the maximum power transfer to the load, and that is the maximum power transfer theorem. On the previous page, notice the Thevenin resistance was 4 ohms, and notice the one that maximized, at least of the different resistors we tried, the one that maximized the power transfer to the load was that 4 ohm resistor. So this example on this previous page certainly doesn't disprove the maximum power transfer theorem, but doesn't prove it because we didn't try every possible resistor. We just tried 5 different resistors here. So we need to come up with a proof that setting the load resistance equal to the Thevenin resistance of the circuit it sees will maximize the power. By the way, matching the load resistance to the resistance it sees is often called impedance matching and shows up in a lot of communications applications, especially in radio frequency RF applications when you're trying to match a load antenna to a system. So let's prove this maximum power transfer theorem. To do this, we're going to use some differential calculus. We saw earlier, a couple pages ago, that in general, the power absorbed by a load is VOC squared times RL over RL plus R Thevenin squared, where VOC and R Thevenin are the models of the Thevenin circuit seen by the load. So what we're going to do now is set RL equal K times R Thevenin. K is going to be our variable. We're going to then take the derivative with respect to K, set it equal to 0 to see what value of K maximizes this equation here. So if you plug in RL equal K times R Thevenin into that first equation, so basically here and here, we're going to plug in KR Thevenin, we get this expression here. This expression on the bottom can be rewritten as K plus 1 times R Thevenin, the whole thing, squared. This R Thevenin in the numerator then cancels one of these R Thevenins in the denominator, and we're left with this expression on the right. To maximize it, we take its derivative with respect to K. So the VOC squared over R Thevenin is a constant, so it stays out. Then to take the derivative of the rest, remember it's a denominator times the derivative of the numerator. The derivative of K is just 1, minus the numerator times the derivative of the denominator. The derivative of K plus 1 squared is 2 times K plus 1. All of that over the denominator squared. That is the derivative of K over K plus 1 squared. We now want to set that equal to 0, which basically means that we're setting this equal to 0, or K plus 1 squared equals 2K times K plus 1. That K plus 1 cancels one of those. You end up getting K plus 1 is 2K, or K equals 1. So we've proven now that this expression is maximized when what? When RL is equal to 1 times R Thevenin. That is the proof of maximum power transfer. The actual power that's absorbed in this case, we plug this value of K into that expression. We get 1 over 1 plus 1 squared times VOC squared over R Thevenin, or 1/4 times VOC squared over R Thevenin. This is the expression for the maximum power that can be transferred to a load when the load is driven by Thevenin equivalent circuit that looks like this. VOC and R Thevenin. And once again, the value of our load that gives us that maximum power transfer is setting it equal to R Thevenin. If we were to plot this expression as a function of K, we get this thing here. So on the x-axis we have K, which is nothing more than the ratio of R load to R Thevenin. And on the y-axis we're plotting K over K plus 1 squared, which is a normalized value of the load power. Remember, the load power is K over K plus 1 squared times VOC squared over R Thevenin. What we see is that for very low values of K, the power absorbed is going to be low. Then as we increase K, the voltage across the load goes up, the current goes down, but we reach a maximum at some point. Where do we reach that maximum? Where K is equal to 1, or when RL is equal to R Thevenin. As we continue to increase the load resistance, the voltage continues to go up, but now because the current is going down and the product goes down, and eventually we'll get back to zero power. For example, when we have an open circuit situation, when RL is infinity, the voltage is equal to VOC, but the current is equal to 0. This is exactly what we observed in the example that we just finished. We have a couple important points I want to make about maximum power transfer. These are a couple fallacies that people sometimes think are the case that really are not. The first one is maximum power transfer does not mean the same thing as maximum efficiency. Maximum power transfer means just that. It is the maximum power that any load can absorb in a given circuit. Maximum efficiency would be the ratio of the power absorbed by the load divided by the power generated by the source. Although maximum power transfer maximizes the numerator, it also increases the denominator. In fact, it could increase the denominator by even more, so the efficiency is not necessarily maximized when maximum power transfer happens. The second fallacy that people have is they think that setting the load resistance equal to the Thevenin resistance of the circuit to maximize power transfer is the same thing as setting the Thevenin resistance equal to the load resistance. So in a normal situation, you don't really control R Thevenin. R Thevenin is the Thevenin resistance of the circuit that you're dealing with. What you have control over is the load. So you change the load, you set the load equal to R Thevenin to maximize power transfer to the load. But what if you have the ability to design a circuit to change R Thevenin? Your first thought might be, oh, if we know that we're going to be driving, for example, a 100 ohm load, let's set R Thevenin equal to 100 ohms to get maximum power transfer. It doesn't work that way. So the rule that RL should be set equal to R Thevenin to maximize power transfer is not the same as setting R Thevenin equal to RL. And we're going to prove that down here. Once again, we saw earlier that the power absorbed by a load is RL over RL plus R Thevenin quantity squared times VOC squared. When we prove maximum power transfer, we set RL equal to K times R Thevenin, where K was some variable, and we found out the value of K that maximized this expression here. Now we're going to do the opposite. Now RL is going to be fixed, and R Thevenin is going to be selectable. What we want to do is see what value of K maximizes that. So now we're going to plug KRL in wherever we see R Thevenin. And we end up getting this expression here. If you then factor out RL from the denominator, you end up getting this expression here. It's clear that this expression is maximized when K is equal to 0. So what we see is that if you have a situation where RL is fixed, but you can change R Thevenin, maximum power transfer does not happen when R Thevenin is equal to RL, but it is maximized when R Thevenin is minimized. In other words, in designing a circuit, you want to make R Thevenin as small as possible if you're concerned about maximum power transfer. So once again, the maximum power transfer equation is for situations where you don't have control over R Thevenin, you only have control over RL. Let's do a couple examples. In this example, we're asked to determine the power delivered to the load when the load resistance equals the Thevenin resistance. In other words, when we have maximum power transfer. Then we're asked to determine the total power supplied by the sources in the original circuit and then calculate the efficiency. So the first part we actually did already. So from before, the Thevenin circuit as seen by the load resistance is what? A 24 volt source and a series 4 ohm resistor. So of all the possible values for RL, the one that will maximize power transfer to the load is by setting RL equal to 4 ohms. In this situation, what is the power absorbed by the load? Using the maximum power transfer equation, it's VOC squared over 4R Thevenin. Which is 24 volts squared over 4 times 4 ohms, 36 watts. This is what we saw, by the way, in this example here. So it's really nothing new. But now we want to find efficiency. To find efficiency, we cannot use the Thevenin equivalent circuit. We have to use the original circuit. Why do we have to use the original circuit? To find efficiency, we need to know the power generated by the sources. If you replace the sources by their Thevenin equivalent, you lose that information. Remember, one of the rules with Thevenin's theorem is you only transform the parts of the circuit that you're not interested in. Since we are now interested in the power generated by the two sources, we cannot use Thevenin's theorem for them. So if we go back to our original circuit, We have a 20-volt source, a 5 ohm resistance there, a 2 amp source, a 20 ohm resistor, and now we know we're going to get maximum power transfer to the load when it is set equal to 4 ohms. But now the question is, we want to find what is the power generated by this voltage source and what is the power generated by that current source. So basically we need to find the current coming out of this voltage source. I'm going to call that I1. That gives us the power associated with the voltage source. And then we want to find the voltage across this current source. I'm going to call that V2, and that gives us the power associated with the current source. So using KCL, let's call this ground here. So you have a node here, value 0 volts. You have another node up here. We can call that V2. And then you have a node here with a known voltage of 20 volts. So if we do KCL at the V2 node, this current plus this current plus this current plus this current has to equal 0. Current to the left is V2 minus 20 volts over 5 ohms. The current going down is negative 2 amps. The current going down here is V2 over 20 ohms. And the current going down here is V2 over 4 ohms. The sum of those currents has to equal 0. Solving for V2, you get V2 is equal to 12 volts. Once you know V2, we can then find I1. I1 is 20 minus V2 over 5 ohms. That's Ohm's law. And that is 20 minus 12 over 5, or 8/5 of an amp. So now we can calculate the power absorbed by the 20 volt source. It's the voltage across it, 20 volts, times the current into the plus terminal. The current into the plus terminal is negative I1. So the absorbed power is 20 volts times minus 8/5 of an amp, or negative 32 watts. So that means that the 20 volt source supplies 32 watts. How about the current source? The absorbed power by the 2 amp source is the voltage across it, which was V2, which is 12 volts, times the current into the plus terminal. The plus terminal is up there. The current into that is negative 2 amps. So the absorbed power is negative 24 watts. That means that the 2 amp source supplies 24 watts. So the total power supplied is 32 watts plus 24 watts, or 56 watts. So the efficiency is a percentage of the power supplied by the sources that's actually absorbed by the load. So the efficiency is that the power absorbed by the load is 36 watts. The power delivered by the sources is 56 watts. It is 64%. Once again, you have to use the original circuit in order to find this power and this power. You cannot use the Thevenin equivalent because you lose the 20 volt source and the 2 amp source in the Thevenin equivalent model. Let's do another example with maximum power transfer and efficiency. So now we're given a circuit with a dependent source, and we're asked to once again determine RL so that maximum power is delivered to the load, and then determine that load power. And then we're asked to determine the power supplied by the sources so that we can calculate efficiency. This is a circuit we also saw before. We can replace everything to the left of the load by its Thevenin equivalent, which we saw was a 5 volt source and a series 5 ohm resistor. So everything here can be replaced by that. As far as the load resistor is concerned, it doesn't know the difference. We can then put in the load resistor, and of all the different load resistors we can choose, if we set it equal to 5 ohms, the same as the Thevenin resistance, we get maximum power transfer to the load. What is that load power? The equation for maximum power transfer is what? VOC squared over 4 times R Thevenin, which is 5 squared over 4 times 5, which is 1.25 watts. What this means, of all the possible values you could plug in for RL, if you calculate the power absorbed, the maximum you're going to get is 1.25 watts, and you get that when RL is equal to 5 ohms. So that's the first part of this problem. The second part of the problem is to determine the efficiency of the circuit. So once again, we cannot use this Thevenin model here. Instead, we have to go back to the original circuit. We'll do this on the next page. The original circuit was a 10-volt source, 5-ohm resistor. We had a dependent source, Ix over 2, where Ix was defined as the current going through the 5-ohm resistor from right to left. We had another 10-ohm resistor here. And then, of course, we stick in our RL, which we saw from before, needs to be 5 ohms for maximum power transfer. There are two sources. There's this independent voltage source, and there's this dependent current source. In order to calculate the power associated with these sources, we need to find the current going through the voltage source. We'll call this I1. And the voltage across the current source we'll call V2. So let's find I1 and V2. I'm going to use nodal analysis. I will define ground. So ground is here. This is all 0 volts. We have a node up here. I'll call that voltage V2. And then we have a node here. That voltage is given. It's 10 volts because of this independent source. So we're going to do KCL at the V2 node. Before we do that, we want to get rid of this current variable Ix. This Ix is a control variable. Ix is what? It is the current through the 5-ohm resistor going from right to left. So Ix is equal to V2 minus 10 volts divided by 5 ohms. Ohm's law. It's voltage at the coming from point minus the voltage at the going to point divided by the resistance. We can now do KCL at the V2 node. We're basically summing up that current plus that current plus that current plus that current is equal to 0. The current to the left is Ix, but once again, we don't want to call it Ix. We want to replace it by its expression that it only uses V2, V2 minus 10 over 5. The current through the dependent source is negative Ix over 2, or minus V2 minus 10 over 5, all of that over 2. Current through the 10 ohm resistor is just V2 over 10. The current through the load resistance is V2 over 5. The sum of those four currents is equal to 0. The only unknown is V2. We can solve for V2. We get V2 is equal to 2.5 volts. Once you solve for V2, you could then solve for I1. I1, which is the same as negative Ix, is going to be equal to what? 10 minus V2 over 5 ohms, or 1.5 amps. Now that we know I1 and V2, we can now find the power absorbed by the voltage source and the power absorbed by the dependent current source. The power absorbed by the voltage source is the voltage across it times the current into the plus terminal. The current into the plus terminal is Ix, or negative I1, so it's minus 1.5 amps. So we get negative 15 watts. In other words, the 10-volt source supplies 15 watts of power. How about the dependent source? The absorbed power for the dependent source is the voltage across it, which we already determined was 2.5 volts, times the current into the plus terminal. The plus terminal is there, so the current in is negative Ix over 2, Since Ix was negative 1.5 amps, negative Ix over 2 is plus 0.75 amps. This is plus 1.875 watts. In other words, the dependent source absorbs power. Because it absorbs power, that power is not factored in when we look at efficiency. Efficiency is what? It's the power absorbed by the load divided by the power delivered by the sources. So in this case, the power absorbed by the load was 1.25 watts. We saw that on the previous page. And the power delivered by the sources, it's only this source that we take into account, 15 watts. And we get 8.3% efficiency. And remember, once again, when we have maximum power transfer, we're not saying anything about this efficiency being maximized. Could other values of RL give us higher efficiency? Absolutely. Can other values of RL give us a higher power? No. The final topic we're going to look at in this packet of notes is the Thevenin-Norton equivalent of non-ideal measurement devices. In lab, for example, you've been using voltmeters and ammeters to measure voltages and currents in the circuit. Likewise, you've been using the oscilloscope to measure voltages in the circuit. And we've always assumed that when we connect up the voltmeter or the ammeter or the oscilloscope to the circuit, that we're not changing the circuit. But that's really not what happens. When you are connecting up a measurement device to the circuit, you are slightly changing the circuit, and you could use Thevenin's theorem to determine how you're changing the circuit. So let's look at voltmeters. So when you use a voltmeter to measure the voltage, you place it in parallel with the device that you're measuring the voltage for. Ideally, that voltmeter would have infinite resistance. In other words, it would not draw any current, and it would not alter the circuit at all. In practice, however, a real voltmeter is going to have a very large but non-infinite resistance, which means that the circuit will be slightly altered when you measure it. But what we're going to see is that as long as the resistance of the meter is much, much larger than the resistance of the part of the circuit that you're measuring the voltage across, the measurement will be close to what the true value is. Ammeters, it's the exact opposite situation. An ammeter is placed in series with the device whose current you're measuring. Ideally, an ammeter would have no effect on the circuit, which means that it would have zero resistance, and it's not going to have a voltage drop. In practice, however, an ammeter is going to have a very small resistance, which means that when you put it in the circuit, it's going to change the circuit. But as long as the resistance of the ammeter is much, much less than the resistance of the circuit element whose current you're measuring, the measurement you're going to get is going to be close to the real value. A good analogy, imagine that you had a scale to weigh yourself, but you had to hold the scale as you weighed yourself. So the weight of the scale would then affect your weight measurement. Now, as it turns out, that's not how scales work, so you don't have that problem, but that is a situation with voltmeters and ammeters. Whenever you use them to measure a voltage or a current in the circuit, you are ever so slightly changing the circuit that you are measuring. So you should be aware of this phenomenon, and you could use Thevenin's theorem to sort of predict how things are going to change. Let's do a couple examples. So let's say that we have a 10-volt source with a very small series resistance connected up to a 100 ohm load, and we want to measure the voltage across the load. There are actually going to be three different voltages. There's the ideal voltage across the load, there's the actual voltage across the load, and then there is the measured voltage across the load. So ideally, VL would be 10 volts. Actually, however, because of the loading effect, because there is an internal resistance associated with the 10-volt source, the voltage across the load will be slightly less than that. So due to loading, the actual load voltage is going to be 100 ohms over 100.1 ohms multiplied by 10 volts. So from voltage division, VL, the voltage across the load, is going to be 100 over 100.1 times 10 volts, or 9.99 volts. This is once again due to loading, because there's going to be current flowing through this resistance, so you get a voltage drop across there, so the voltage you get at the load is not quite 10 volts. But now we're going to take it a step further and we're going to look at the measured load voltage if we put in a voltmeter. So now we have this situation. We not only have this internal resistance of the source that we have to take into account, we now have the resistance of the meter itself. So when we stick in the voltmeter, and in this case we're told the voltmeter has a resistance of 10 kiloohms, we're changing the circuit. So the very process of measuring this load voltage changes the circuit whose voltage you're measuring. So in other words, this 10 kiloohm resistor here is the Thevenin equivalent of that voltmeter. We can now analyze this circuit here by putting the 10K resistor in parallel with the 100 ohm resistor. So we have 10 volts, 0.1 ohm. This resistance here is now 100 in parallel with 10,000, or 99.0099 ohms. So the VL measured is that resistance over the sum of those two resistances times that. So VL measured is 99.0099 over 99.1099 times 10 volts, or 9.98991 volt. So you have three different situations. Ideally, if you ignore the loading effect and ignore the voltmeter itself, you would expect 10 volts across the load because you're connecting a load up to a 10 volt source. If you take into account the loading and the internal resistance of the source, the actual voltage you're going to get is 9.99 volts. And finally, when measuring the voltage across the load, we need to take the resistance of the voltmeter into account, and the actual measured voltage is even going to be less, in this case 9.98991 volt. One thing we see here is as long as the Thevenin resistance of the meter is much, much larger than the resistance that we're measuring the voltage across, you're not going to have much of an effect here. If Rm is much, much greater than RL, because remember, a load resistance in parallel with a very large number is approximately equal to the load resistance. Let's look at an example with an ammeter now. So once again, let's take a voltage source and now drive a 100 ohm load with it and calculate the ideal, the actual, and the measured current through the load. So ideally, if you take a 10 volt source and drive a 100 ohm resistance, IL would be 10 volt over 100 ohm, or 0.1 amp. But actually, due to loading, we get what current? We get a current of 10 volts, not divided by 100 ohms, but we have to take this 0.1 ohm source resistance into account. So 10 volts divided by 100.1 ohm, or 0.0999 amps. So once again, this is the actual current that we get due to the loading effect. But now, if we stick in an ammeter to measure that, we have another thing that we need to take into account, and that is the internal resistance of the ammeter. So the measured current is what? We redraw the circuit, taking the internal resistance of the source into account, now adding the resistance of the ammeter, which we're told in this problem is 0.05 ohms, and then our load resistance, 100 ohms. So IL measured is going to be 10 volts divided by 100 plus 0.05 plus 0.1, or 0.09985 amps. So once again, just like with the voltmeter case, we have three different situations. Ideally, the current we would want would be, from Ohm's law, 10 volts divided by 100 ohms. If you take the internal resistance of the source into account, the actual current you get is a little bit less, But then when you try to physically measure it by sticking an ammeter in there, the ammeter changes the circuit, as we see there, and so the actual current you get is even less than that. Once again, if the internal resistance of the ammeter is very small compared to the resistance of the load whose current you're measuring, the effect of that ammeter resistance is going to be very, very small. So it's opposite of the situation with voltmeters. With voltmeters, you want the resistance of the voltmeter to be much larger than the resistance of what you're measuring. In an ammeter, you want the resistance of the ammeter to be much less than the resistance of what you're measuring. That concludes this packet of notes dealing with additional analysis techniques, where we first talked about linearity, then superposition, then Thevenin's and Norton's theorem, and then finally a couple applications of Thevenin's theorem. Have a good day.